Okay, so the first thing I want to say is homework 2 is up, as are the lecture slides and videos. Just a reminder, week 1, remember we got kicked off of, lecture 1, we got kicked off of Canvas. So what happens when they kick you off is everything was lost. So that's why there's no video for lecture 1. And there's no slides for me to upload. So I apologize about that. I mean, you didn't miss anything. Well, yeah, you did. You missed fun. So homework 2 is a little longer than maybe the first one. So I would try to get started on it now. That way you can ask questions Monday or through email and stuff like that. Very good. Does anybody have a question at all right now about anything in particular? Whether it's homework, some of the stuff we've been doing. I'd be happy to answer anything. No? Okay. Okay, so here we go. Why is this not working? So where did we finish off last class? So last class, what we did is we discussed propositions that depend on variables. So, for example, P of x, and then what will P of x be? Let it be the statement x squared greater than x. So the truth of this statement depends on what is x. So what I mean by that is if I say P of 3 is the statement that 9 is greater than 3. This is true. But P of, say, 1/2 is the statement 1/4 is greater than 1/2, which is false. So think about that for a second. And if you have a question about it, let me know. Now, I would encourage you to ponder these things in sort of, again, this is a class that is technically a math class, right? This is, I mean, even though we're running it through the computer science department, this is a math class. So much of what we do, we're going to do it through the lens of mathematics. However, many of these things are cross over very easily and in a very important way to things like programming and computer science. Imagine a computer program that a lot of times what you're going to want to do is if the user does this, then that. Or if this is true, then this task must come next type of thing, right? Or if this is false, then you do this. And so in many ways, when I say something like is x squared, we're going to talk about things like, when is x squared greater than x, or is it true, is it false? Well, you can imagine scenarios where this is the same thing, the same idea is used in another sort of context, okay? Okay, good. Does anybody have any questions about this particular sort of first page? So hopefully what you're doing is you guys are reading the book. A reminder, I didn't make it mandatory that you buy the book, right? But I would encourage you get it. If you Google it, it's there, free PDF version. And so I would highly encourage that you do that. It's your earliest convenience, because it's really, again, you need to sort of, in my opinion, you should be following along in the book. There's a lot of details the book covers that we just can't cover in lecture, right? I mean, it'd be impossible. So, and there's also a lot that the book covers that we're not going to be requiring you to know. I mean, at the same time, though, this is up to you how much of it are you interested in covering. Okay, so when we have statements like this, one of the things that might be obvious, not obvious, but at least of interest to us is so we're going to use what are called quantifiers to aid in the problem-solving process. So what is a quantifier? Well, a very intuitive way of thinking about this is we want to have symbols for English words that tend to come up, for example, in mathematics a lot. So I want to consider two scenarios with the previous example that we gave, all right? So let's think of just English sentences first, and then what we're going to do is sort of try to translate it to some mathematical language. So here we're going to have a true statement, and it's going to be there exists a real number x such that x squared is greater than x. So that is a true statement, is it not? I mean, I just exhibited it one, right? 1/2 makes this a true statement. There's lots of in fact, any number between 0 and 1 will make this a true statement. Any number between -1 and 0 makes this a true statement. So the thing you should note is if x is between 0 and 1, or -1 and 0, this is true. Now let's look at another sentence that is patently false. For all real numbers x squared is greater than x. That is clearly false. Why do I know it's false? Well, I just showed you that it was false because I gave you a bunch of examples where it's true. Or excuse me, let me rephrase that. This statement is false is because we found, at least in our mind, we would say it's false because we're going to say intuitively. Think intuitively now. So Carly, say you go to me, you go, O'Grady, every single real number x satisfies x squared greater than x. And then I would say, no, you're lying to me. You're making up a lie. How do I know you're making up a lie? You're making up a lie because I can find at least one guy who proves you're lying, right? Yes?
I don't understand the note. Shouldn't this be false if x is between 2 and 1?
No. Take number 1/2. What's the square root of 1/2?
1/4.
Mm-hmm. Right? So then what should the correct thing be?
This is false.
Well, no, it's not. There exists a real number. So okay. So we're paying attention. That's good. So if we take the eraser, what should the note actually say? The note should say, if or when x is less than -1 or x is greater than 1, this is true. Does that make sense? Okay, very good. We're paying attention. Does that make sense now, Abdullah? You good? So the phrase is there exist and for all. They come up often. And we want symbols for them. That's what we want to do. So we want a mathematical symbol that we can use for the words there exist and for all. Did you miss too much? No. Even if you did, what's it matter?
I thought I had online today. So
That's okay. All the stuff will be online. You're all right, Josh. We'd have to get you an assistant to make sure you're in the right place at the right time. So, let's give these names. So, so let P of X be a proposition. We call there exists X such that P of X, we call this the existential quantifier. So it's denoted with a backwards E, P of X. So another way to think about this is the following. When you see this backwards E, PX, this reads, there exists an X such that. Does that make sense? So you can think of this as a shorthand for an English phrase. Instead of writing out there exists in propositional logic, we don't want to use the English words. We want to use symbols. Some people think this is good. Some people think it's bad. Nonetheless, one of the things in your major you're asked to do is learn it. So instead of saying there exists, we write this backwards E. Now, in your limited math experience, you guys have seen this already. An example of an existence theorem was what we call the intermediate value theorem, if you remember from calculus, where we say if a function's continuous and at one endpoint of an interval it's positive and at the other negative, then there must exist a point where it crosses the x-axis. So all we're doing is telling you it exists. We don't tell you what it is, we just tell you that it exists. All right, does anybody have a question or a comment about this? Very good. So there's the other quantifier we saw is this for all. And so that's what we're going to cover now, what we call the universal quantifier. So what is the universal quantifier? Well, this is so this is denoted by, this is like an A, but it's sort of like upside down. So how does this read? So the way you read this, when you see this upside down A in front of a statement, you read it as for all x, P of x, whatever that statement is. And then if you see it for, or you could read it for every x. Now here's a very important word that we're going to use oftentimes. Any element x that makes for all for all x, P of x false is called, creatively enough, a counterexample. This is very important when you think of logic. Let's sort of go back to what we were talking about with the previous example with x squared greater than x. If I tell you that's true for all x and you want to prove me wrong, you don't have to list 5 things that make it false. You just got to find one. And we call that example, or any one you find, we call it a counterexample. That's very, very important, not just in mathematics, but in the science of computers, which we call computer science, and also in coding, programming. Now, we want to give meaning to when these things are true and false, and we want to do it in a very logically sound way. You guys, we know that if I write for every x, x squared is greater than x. Well, first off, there's a couple subtleties there. What are my allowed values of x? So this is where the word domain comes back into play. Remember, when we talk about functions, the amount of the values that we're going to actually consider matter. So let's make sure we make a note of that. So before we do anything, let's note context matters. Now let me be very, very clear what I mean by this. Let's go back 2 pages or 3 pages. Notice that I was very clear on what I was expecting x to be. What was x? A real number. However, if I restricted my quote-unquote domain, then it's possible that I'm not lying to you. Are we clear? Now, in the way that I've written this sentence, I'm not lying to you because I was very clear on what x could be. The only possibility for x, it couldn't be a cat, it couldn't be a dog, it couldn't be a complex number, it could be a real number. So let me explain what I mean by context matters. So the statement for all x, x squared greater than 1, or excuse me, x squared is greater than x. This guy is false if so let me be very clear. Let me be a little more clear with my language. This statement is false if we allow x to be a real number, or if we are, you know, maybe that's a bad way of saying it too. If we assume but if we change the roles slightly, the statement for all n squared is greater than n. This is true if we assume n is a positive integer greater than 2. Right? Because what would then be the options there? If I say you're a positive integer greater than 2, then your options are 3, 4, 5, 6, and those we can at least intuitively say they're all true there. Now we'll get into the deeper problem of how do you know that for certain, but at least intuitively. Does anybody have a question about this, a comment, a concern? I need some scissor. High fructose corn syrup, as it were. Are we okay with this when I'm saying context? So the context of the problem, what are you allowing the allowable variables? So let's make a note of this because we didn't quite define it yet. So for any P of X, we call all possible values of X the domain. Just like when you're talking about a function. So it's useful to sort of summarize the truth values here in a truth table, or maybe not a table, you can call it a chart if you will. So let's summarize this real quick. I'm going to change my color here. So if we take the statement, there exists X, P of X. So and then we take the statement for all X, P of X. Let's make a little table to illustrate what's happening here. Well, I guess I should use straight lines. That would be more cumbersome for you. So here, this column will say it's when it's true, and this column will say when it's false. So when is there exists true? When is this true? Well, all we need for this to be true is there's at least one value in the domain that makes px true. So maybe I should lower this since I didn't judge my, didn't plan ahead. And then when would it be false? It's only false when P of X is false for every X. And then of course we would imagine that the reverse would be true for the universal one. This is true when Px is true for all X in the domain. And it's false when there is at least one X in the domain that makes P of X false. So this is sort of a good chart to have in your back pocket. We will use it a bunch, and some of you will use it a bunch more even after this class when you're in advanced mathematics courses. So once again, we have to then make a point to the idea of when, you know, obviously we can build statements that have multiple quantifiers. In fact, You've seen that if you ponder some of the things you've learned in math already. And so then the question would then become, what order do we operate on them and all that? And again, how do we avoid ambiguity? We use grouping symbols. And this is a skill. Learning how to translate from English to symbols and from symbols to English is a very difficult skill to learn. No one's going to expect you to be really, really good at it at the end of this semester. But it's something that you want to be better at as the semester goes on. You want to improve. And the bad news for some of you is the only way you improve is by doing it all the time. This stuff can be very confusing to learn. So one important thing we do is we negate. So we want to be able to negate quantifiers from time to time. So for example, we might have the statement there exists x such that x squared is greater than x. Well, what's the negation of that statement? The negation then would be if you have to think in terms of true and false. So we know that's a false statement. So how can we rewrite that sentence so that it's true? So again, let me repeat. There exists an x such that a statement is. So let's take that example. So consider there exists x such that x squared is greater than x. What should the negation of this be? So there's a couple of ways we can reason what the proper way to handle this is. And the first thing I would tell you to do is note that this is true when x is real. So let's say that in English, there does not exist an x such that x squared is greater than x. How could we rewrite the sentence? So now I want you to consider this statement, which would be for all x, negate x squared greater than x. Well, what's the negation of x squared greater than x? Well, you can be picky, but you might say that this is quote unquote equal to the statement for all x. What's the opposite of x squared greater than x? You might say x squared less than or equal to x. Yes or no? So in general, and this is going to sort of, this might sort of be scary. In general, the negation of there exists x px, this is actually logically equivalent to, for all x, the negative of p, the negation of p. And then similarly, if you take the negation of for all x p of x, it is logically equivalent to there exists x such that negative p. Now you could verify this with truth tables if you wanted, or you can think of it sort of as just, you know, that's up to you how you want to do it. I would encourage you to try to verify this, whether you use an example from English words, whether you use an example from mathematics like we did here. So you'll notice that the negation here is false of this statement. So look at the statement in the last sentence that was written in black. So if I say there exists an x such that x squared is greater than x, we know that's a true statement. But let's also verify in our brain that the negation of that. If I say there does not exist an x such that x squared is greater than x, you're going to say, you're lying to me. That's false, O'Grady. I can find one, right? Now look at the last sentence in red. Is that true or false? Well, that's also going to be false. You can easily find an x that its square is bigger than x, right? So what we're saying is it's two ways to write the same thing. This goes back to the example I've used before. On Monday, I said, Fink is younger than O'Grady. O'Grady is older than Fink. That's two English sentences that describe the same fact. There's a very analogous idea happening here. Two sentences that describe, at least logically, the same fact. Does anybody have a question or comment? Everybody overwhelmed, annoyed, scared, all that fun stuff? It can be funny. You all worried about going to graduate school already? All that fun stuff. You should be worried about this. Be a teacher. What you should worry about is going to find some school board members in a real nice school district that pays well and don't have a bunch of crazy parents and then go, you know, asked to do whatever. You still babysitting? That's fun. Making that De Niro. All right. So, very good. Does anybody have a question about this? Okay, so there's lots of things that sort of, you know, that, again, how we learn this is different for each one of us. Some of you will pick this up quicker. Some of you will take a lot of effort to pick it up, and you'll still have what we call imposter syndrome. You won't believe that you actually get it. You'll say, I'm not smart enough for this. That's what people will say. I'm not smart enough for this. Now, that's a silly thing to say. This is hard to learn for all human beings. It is. Now, there's a few people on this planet that just get this stuff. And that's okay. We let them live their own little lives, right? We are mortal humans, and we're normal. And so what we often have to do is we often have to suffer to learn this. But the suffering's not all bad. I mean, I've said this to you guys numerous times, and I really believe it. The process of learning and the process of, in my opinion, what makes math fun is there's a whole learning that happens even if you don't necessarily solve the problem the first 10, 20 times. There's learning to be had in the process, not just the final result. So you got to keep that in mind, put things in perspective, all that fun stuff while you're doing this, and don't stress too much. Very good. Okay, so these quantifiers often come in pairs. Such as, for all x, there exists y. So let's look at a famous example from your childhood that you learned about from a mathematical background. For all x, there exists y such that x plus y equals 0. So if x and y are real, this is true. Well, why? So here's how we're going to read this. How do we read in English? What direction do we read? Left to right, correct? So if we translate this to English, this means pick any x, because this, if it's going to be true for any x, right? So pick any x. There exists a y, and what is y? Well, namely, what is it? What's the fancy word for y? Well, does anybody remember what this is called? What we call y. So when you first learn about numbers, you learn that every number has a additive and multiplicative what? Don't overthink this. What's 5 plus negative 5? What's 7 plus negative 7? What's negative 7 plus 7? This is called the additive inverse. Every number has an additive inverse. Whew. So the point is, pick any x you want. For every x, there's always going to be a number y that satisfies this. This is called the additive inverse. I just showed you it's true all the time. I mean, we didn't really talk about what a proof is, but I'm not lying to you. Pick any number you want. Pick your favorite number. What's your favorite number? 3. Okay, guess what? 3 plus negative 3 is what? 0. Works. Spend the rest of your life doing this for numbers. And since it's clearly we can always choose y to be the minus of whatever x is, it's always going to work. Pick say your x is negative 10. What would y be? It would be negative 10 or plus 10. Negative 10 plus 10 equals 0. Does anybody have a question about this? So in many scenarios, we have a proposition that depends on two variables. Say it's P, and then how do we illustrate to the user that it has two dependencies? We call one X and one Y. I mean, we could use any letters really, but it's common to use X and Y. Then the statements, for example, you might have for all X and for all Y, P of X, Y, or if you switch it for all Y and for all X, P of X, Y. And then you could, you know, how many statements are we going to have? Well, if we have two different variables and we have two of these quantifiers, well, we have to run through all the different scenarios. So what's the next scenario? Then other scenario you could sort of envision is there exists X, there exists Y, or there exists, I guess I should say, there exists Y, there exists X, PXY. And then the two ones that would come in the middle is the ones we just did. For all X, there exists Y. And then, of course, the sort of the opposite of that is there exists X such that for all Y, P of XY. So, I'm not going to write the table down. I'm guaranteeing it's in. I know it's in your book. You should read it. You should read about these in section 1. What section would it be? So it would be section 1.5, I think. Yes, it's going to be 1.5 because 1.7 is proofs, 1.6 is inference. So you should read about these. I mean, again, I could list it, but I don't know that that's. I could draw the table out. I don't know how useful that is right now. These things are a little more complicated than to just look at a table and say, "Oh, it makes sense." You should read the sort of the verbiage that comes around the table. You should look at mathematical examples that the book gives. You should look at English sentence examples that the book gives. And then you should even try to create your own. And think about how do we translate these things. You know, the way you got to learn it is you got to try these things, and then you got to get a feel for it, and then you got to ask questions, right? So, for example, if I pull up the homework, hopefully you guys are seeing this right now. So is everybody seeing, hopefully you guys are seeing Canvas on your home, on the computer. So if I go to the homeworks, you know, there's a lot more in the book than we would actually, any normal person would cover. So I'm not making you responsible for everything. It's not like I'm skipping it. It's just that it's too dense. I'm encouraging you to do all the reading and stuff like that. But what you should be feeling like, what do you need to have for a test? In the past, I've always made this clear. It's your homework type stuff, right? What do I assign on the homework? And so you'll notice what I find important is certain things. And I think what's most important for you right now is to understand things like this. Not that you can recite definitions or recite them off the table, but that you can make sense of these things. And what you're going to have to do to determine the truth value, for example, in problem 5, is you're going to have to refer to that table until you get a feel for, and some of you might not have to. Some of you get instincts for these things. I mean, the truth value of these things are very instinctive. It's just for every one of us having a different human brain, we need to see, every one of us needs to see a different type of example before it clicks. Some of you, it clicks on an English example where we use English sentences or words. For some of you, it takes a specific math example. For some of you, things I do might not help at all. It might, again, every one of us is different. So you're not all going to learn it from the same examples. For some of you, it will click right away. For others, it's going to take some time. So you have to realize that when you're trying to learn this. Does anybody have a question about this? So if we go back, we can maybe look at some stuff that will help you with your homework. So what I'd like to do is instead of just, instead of reciting these rules, anybody have anything they wanted to say? Comments, concerns? So let's do a couple. So first one we're going to do is the following. For all x, there exists a y such that x is equal to y squared. So let's translate it into English first. That might be helpful. For every x, there exists a y such that x equals y squared. So how do we answer this? Well, we got to ask ourselves, do we think, is it intuitive to us? Is it, and oftentimes, if nothing comes to you right away, a good strategy is to try to look for counterexamples right away. So what would a counterexample mean here? Well, you have to think from a logical standpoint. I'm telling you, the promise I'm making you is that if you pick any x, you can always find a y, such as this is true. So one way to break that promise, at least intuitively, and it's also logically correct if you, and you can reason this for yourself, is that if you pick an x, you can't find a y. Now, you could go through the, I don't want to say torture because it's good practice, you could go through the idea of negating this and seeing if that's easier to verify. Or you can look for counterexamples. There's multiple strategies here, and every one of us might take something different. I'd like to think of this as a promise that is either kept or not kept. So what do I mean by that? Well, I'm telling you, once again, that if you pick a value x, and someone's chatting, okay, so Ethan's on to something here. We'll look at that in a second. So we're saying, and if we even translate more English, we're saying, and maybe you can even, another thing that's also useful to do is to rewrite the expression equivalently. Pick an x. Is it always true? So imagine you have an equation, pick an x, pick a number, say you pick 10. Well, how would you find out what the corresponding y would be? Well, one thing you could do is take the square root of both sides, and you say, oh yes, y would be the square root of 10, right? And say it worked for 10. Now that's not a proof, that's nothing. However, an example can count as showing you that it's false, because all you need to show that it's false is one counterexample. That's it. So as Ethan pointed out, it's not that you want to take x greater than or equal to 1. You want to think about it slightly different. What if I tried that same reasoning on I pick some random x, for any x it's supposed to be true, right? What if I pick -1? Is there any real number y that satisfies -1 is equal to y squared? No. What do we know about all real numbers? If you square them, they are what? Positive or negative? They're positive. So this is false. And let's explain why. Because if x equals a negative number, so I can even say, that can be general. I'm giving you infinitely many counterexamples. So if x is less than 0, there is no corresponding y. Does that make sense? Now let's look at a very similar statement. What time is it? 12:04. We're going good. Now let's say for all x there exists y such that x squared is equal to y. So now I've reversed the role of the exponent. So now to get a feel for what's happening, let's once again just pick some number for x, because it can be any number. So let's start with something simple. Let's start with 4. So now if I replace x with 4, is there some y out there? I only need one, because I just get for all x, there exists y. So when I pick my x, is there one y out there? So if I let x equal 4, I get 16 is equal to y, right? Is there a number 16 out there? Yeah, right, of course. Now you might say, okay, in the previous example, we realized the negatives messed us up. Well, let's take a negative number now. What if we took negative, say, 10? If I put negative 10 out there, is there a number such that it's real and it's equal to 100? And the answer is yes, it's 100. And we can even be more specific. So this is true. Why? Because once we pick x, we can square it. And basically this statement is just saying that you can square any real number. That's all this is saying. So maybe I'll even be more specific than that, because the square of any real is a real. That's all this is saying. It's saying if you square a real number, the output is a real number. That's what this statement is saying, if you think about it that way. Does anybody want to comment on this, ask a question? So this is the kind of stuff we want you to do on the homework on some of those problems. And so the last thing we ask you to do on the homework is to sort of use these ideas we've been building up. And these are also, the fancy word for this is the rules of inference. Remember, what is our goal? Our goal is to be able to provide logical reasoning to mathematical arguments. For example, we want to be able to state a theorem. We want to say if this, and this are all true, then this must be true. Or logically, in another scenario, this must be false, something. So one of the most basic types of statements in mathematics is this: if this, then that. And we want to be able to give logical arguments to these things. And so there's lots of ways we're going to be able to do that, and we're going to do lots and lots of examples in this class, and hopefully you'll get better at it. You're going to stink at it at first. Everybody does. I stunk at it. You're going to stink at it, right? So one of the things you have to get out of your mind, as I've said numerous times, is no one gets this stuff in 5 minutes. They just don't. And again, I will also emphasize that what I've said to many of you over the past few terms, and it's very, very true. I think I even said the quote, one of the famous quotes about mathematics is that a mathematician isn't someone who is good at math or to whom math comes easy. A mathematician is to someone who enjoys the process of problem solving. I mean, you think about it, as a mathematician, when I was in my PhD program, I worked on the same problem for like 3 years. 3 years. That's what analysts and Google do, and these mathematicians at universities and whatever. They don't work on a problem that just might take 5 or 10 minutes. Oftentimes it takes years and years of trying the wrong things until something comes. And yet you guys get upset when you don't understand this in 5 minutes. And it's not your fault. You've been conditioned that way because the way math is taught in schools up until this point, you say, okay, let's learn this today. And then you go home and do it 50 times. And then tomorrow we'll learn something new. You go home and do it 50 times. And that's not really good, because all that's really doing is preparing you to be a real, SITTY calculator. You're not very good. You're just a procedures. You're not using your mind. You're not thinking. And so what we'd like you to do is we'd like you to learn how to be a thinker. And part of that is recognizing that this stuff is not easy. And I've said that to you before. I mean, many of you, I told you, if you want to be a science major, particularly what we call the hard, not in the sense that they're harder than other things, but the natural sciences like chemistry, biology, computer science, mathematics, you have to realize that it's not about how smart you are. Of course, that helps. Just like being fast helps you play sports, right? Or being strong. Of course, that helps. But it's mostly what it comes down to is how willing are you to sacrifice time to learn hard things? Because that's what you're doing. It takes time to learn these things. And so you have to remind yourself of that over and over and over again. And I hope you do, but I can't guarantee that you will. So the way that I think is best to proceed when I teach this class is there's two sections that sort of follow what we've been talking about. And they talk about these rules of inference. And I feel like it's a lot of overkill for what we're interested in this class. And so what we're going to do is, like, for example, section 1.6, I encourage you to read it, but we're not going to talk too much about it right now. What we're going to do is we're going to interject as the semester goes on of where these ideas are being used when we construct certain ideas. You know? So a good example of that is what I gave on your homework about what was the problem. I said, like, something about everybody in here, computer science major takes discrete math, right? And so something, I think 2 chains, right? So let's look at a similar problem. It's slightly different as an example. So which one did I give on homework? I don't want to give the same one because that's no fun. Yeah, it was the 2 chains one, I think, right? Is that what I gave you?
Yeah, that was it.
Yeah, that was it. All right, good. Nothing like bringing 2 chains into to class. Okay, so let's say a bike is fun to ride. All right. O'Grady, let's be a little more specific. That way we're not we don't want to cheat, and we'll be done. So a 2-wheel bike. O'Grady's bike has 1 wheel. It's a unicycle. Therefore, O'Grady's bike is not fun to ride. So let's think about the reasoning in here. Is the conclusion that my bike is not fun, can that be deduced from the previous 2 sentences? No. You cannot deduce that it's not fun to ride just because it only has 1 wheel. So even if you assume the first sentence is fact, that a 2-wheel bike is fun to ride, that doesn't necessarily mean that a bike that has 1 or 3 wheels is not fun. Do we understand that? So the point of this problem and the point of other ones is making poor conclusions from given information. So really, you might think it's silly, but I think these things are really important to think about. I highly encourage that you do. I don't know that you will. I will beg you to do it. But will you? I don't know. All right, does anybody have any questions, comments? We'll stop here. I will upload the lecture stuff for you guys. Thank you very much. Please work on this homework so you can email me with questions. And then we can talk about anything you might have, because on Monday we're going to start with some math proofs. Thank you guys very much. Be safe.